and in chapter 28, we are going to go back to, the source of magnetic fields, like how magnetic fields are really created. The first thing that we are going to, study is how to calculate the magnetic field produced by a single charge. Then we know that moving a charge or like a current is gonna be creating a magnetic field, and therefore we are going to study how to calculate the magnetic field produced by a single moving charge particle, or by a straight current carrying wire, or a current carrying wire bent into a circle. Then you should know all these and what are really the formulas that we are using for the calculation. Why wires carrying current in the same direction attract, and the other, when they are in opposite direction, they repel each other. And also we are going to study Ampere's law and how to use it to calculate the magnetic field for currents that they have symmetrical distribution, and how microscopic currents within materials give them their magnetic properties. Here, looking at this picture, this is really is a current carrying coil or solenoid. We're going to study the solenoid that generates a uniform magnetic field in its interior as part of an experiment at CERN, the European Organization for Nuclear Research. And what can we say about the magnetic field due to a solenoid? Is it uniform? Is it not uniform? Depends on what actually creates magnetic fields. And also we are going to introduce Ampere's law and use it to calculate magnetic fields. Now, a moving charge generates a magnetic field that depends on the velocity of the charge and the distance from the charge. Then here we have, I would say, a charge, and actually when it is across like this, then this means that the charge, it is moving into the plane of the page away from us. And we can use the right hand rule again for calculation of the direction of the magnetic field. Now I will say the thumb. Okay, let me write here. Oh, what? Okay, then the thumb is gonna be the direction of the velocity, and then curl, fingers, they are going to give you B. Now the magnetic field due to a point charge with constant velocity is B equals mu zero. Mu zero, we call it the magnetic constant. It equals 4 pi 10 to the negative 7. Q is the charge, V cross R, and R here, it is a unit vector from point charge toward where the field is measured. And R is the distance from the point charge to where the field is measured. All right, and now we are going, like, I will apply, of course, this by the end by problem solving. Now also we can find that if we have several charges, then we are going to find out what is really the resultant of these fields, and then I will say B total is gonna be B1 plus B2 plus B2. Then it's like, again, this is like the resultant thing. Now, magnetic field of a current element. Now, what if I have not like a charge? I have a wire that is carrying current, and that the current directed into the plane of the page. Again, for calculation of the direction, we're gonna use the right hand rule. and the total magnetic field of several moving charge is equivalent, of course, to what we have in here, which is electric current. And we can use the magnetic field caused by a short segment of a current using what is called law of Biot and Savart, these like two scientists. And then dB, and then we're going to integrate dB equals mu 0 over 4 pi IDL times r unit vector divided by r squared. All right, now currents and planetary magnetism. The Earth magnetic field, it is called by currents that they are circulating from the molten interior of the Earth. These currents are stirred by our planet's relatively rapid spin, and I will say this causes the magnetic field of the Earth. The moon's internal currents are much weaker. It is much smaller than the Earth, and actually mostly dominantly we have a solid interior. Hence the moon's magnetic field is only 10 to negative 4 as strong as that of the Earth. Now here we can actually calculate the magnetic field of a straight current carrying conductor. We are going to assume that there is a segment that is, we call it DL here, like a small segment. And this is here to display how we are going to use the law of Biot and Savart. And then we want to calculate the magnetic field at this point P here. And we need, of course, to draw the unit vector. We need to calculate what is r, the distance, which is, of course, using Pythagorean, r equals square root of x squared plus y squared. The direction of the current, it is upward. And we will find B at a point that is at x here. Like at x from the origin. Now, since the direction of the magnetic field from all the parts of the wire is the same, we can integrate the magnitude of the magnetic field and obtain that it is going to be B equals mu 0 I over 4 pi 2a x square root of x squared plus a squared. And this is really here showing you that this is the magnetic field of a straight wire that is carrying a current I. Let me do something here. Okay, as we're gonna find that as we are really having the length of the wire is going to be longer and longer and longer, which means x is gonna be very, very large compared to a. And I will say since a is gonna be like related to the length of the wire, then the distance is gonna be replaced by r, and is gonna be to indicate that this is a radius of a circle centered on the conductor. And then b is gonna be mu 0 times I divided by 2 pi r. Now we use this one for what is called long straight, and this is an equation that we are going to use frequently. We will say this is long straight wire or conductor. Again, using the right hand rule, as we said, we can use to find the directions by having the thumb pointing in the direction of I, and then we curl the fingers in the direction of the magnetic field. Now, of course, here magnetic computer cables or cables for audio video equipment create little or no magnetic field. This is because within the cable itself, we have closely spaced wires, and they are carrying currents in both directions to cancel the magnetic fields. They're gonna create opposing magnetic fields, and they're gonna cancel each other. Now, if we have two of these long straight current carrying conductors, we're gonna find that the magnetic field of the lower exerts an attractive force on the upper wire, and if the wire had current that is opposite to the directions, they will repel each other. Now, we can calculate the force between these two conductors, and we're gonna say that we can calculate the force per unit length, and that is gonna be mu zero I times I prime divided by 2r. Here, this is the force per unit length, and I, it is gonna be the current in conductor number 1, and I prime the current in conductor number 2, and then r, it is the distance between the two. And you need to know that this force is going to be attraction if the currents are in the same direction, and is going to be I will say repulsion if they are in the currents are in opposite direction. Definition of the ampere. The SI definition of the ampere. Ampere, remember, it is one of the standard units in the SI system. 1 ampere is that undervarying current that, if present in each of the two parallel conductors of infinite length and 1 meter apart in empty space, okay, so that we can use mu zero, causes each conductor to experience a force of exactly 210 to the negative 7 newtons per meter of length. This definition of the ampere also leads to choose the value of mu zero to be 4 pi 10 to the negative 7, and its unit, it is Tesla times meter divided by ampere. SI definition of the Coulomb is the same amount, is the amount of charge transferred in 1 second by a current of 1 ampere. Because remember, charge, let me say current is defined as delta Q over delta T. And therefore, delta Q is going to be delta T times I. Now, what if my wire, it's not straight, it is a circular conductor that has a radius A carrying a counterclockwise here current in the direction? We can also calculate the, the magnetic field of that conductor at a point B here, and we can find that this here for whenever we have a circular loop, that is the formula that it depends, of course, on the radius of the loop itself. And of course, it has to do with the current as well that is going through the loop. And here, when we do the calculation, we will consider what is called the symmetry of the loop. And I will say, whenever we have it, like we can say that the magnetic field is gonna be canceled, like the y components, and keep in here the x components. This is at any value at x distance from the center of the loop. Now, okay, like this distance x. What I was going to say, yeah, a, it is the radius of the loop. And as you can see, of course, that magnetic field depends on I, depends on A, depends also, of course, on the distance. Now, again, also the direction is given by the right hand rule, and the right hand rule is gonna here, we are going to reverse it. We are going to say the our fingers, they're gonna be in the direction of the current, and then the thumb is gonna show the direction of B. And this is the equation that I did write for you. Bx equals mu 0 I a squared divided by 2x squared plus a squared over 3 over 2. And then we can, if we want to find what is the magnetic field at the center, then x is going to be 0, and then b is going to be mu 0 I a squared over 2, and then x squared is going to be 0, then this is a squared times 3 over 2, then this is going to be a cubed, and then it's going to be mu 0 I over 2a, because it's going to cancel. Now, most of the time, to have like a magnetic field that is strong, we are going to add more turns. We are not using just a single loop, and therefore we will add here the number of turns. Okay, then this is gonna be for a circular loop that has n number of loops. Magnetic field lines of a circular current loop, here showing you the what is really the you know the direction of the direction of the magnetic field. We need to know here that the magnetic field is not uniform. Okay, and we can find usually by the right hand rule the direction using I would say the right hand rule at the center. MRI, it is magnetic resonance imaging, requires a magnetic field of about 1.5 Tesla. And in a typical MRI scan, the patient lies inside a coil that produces the intense field, and the currents required are very high, so the coils are bathed in liquid helium so that it will be cooling the system. Now, Ampere's law, it's very similar to Gauss's law, where we are going to relate here electric current to the line integral around a closed path. And here we're going to say, shown in the special case of a circular closed path centered on a long straight conductor wire that is carrying I, that we can say the integral is going to be integration over a closed surface B dot dl. And then we will have, of course, B parallel dl, because we will have the components in the direction of dl, and from that, when we will integrate dl here, is going to give us the 2 pi r, and B, it is mu 0 I over 2r, and from that we're gonna get mu 0 times I. Also here, the general statement, it is if we have general, we have more than one straight conductor, they are passing through a surface, then we can say the line integral of the total magnetic field is proportional to the algebraic sum of the currents. Then you're gonna say what is in, what is in out, and you're gonna curl the fingers of your right hand rule of your right hand to around the integration, and your thumb points in the direction of the positive current. Okay, for the general statement, we like it's very similar, as I said, with Gauss's law. We added the word enclosed, then the algebraic sum of the currents enclosed or linked by the integration path with the sum evaluated by using the right hand sign rule, which is pointing for the currents. And then here we can say, for example, for this one here, any current that is now out of the page is going to be positive, isn't it? Okay, here. Okay, I1. Okay, and I2 is going to be into the page. Okay, the anyone is the, okay, here. Okay, yeah, out of the page is going to be positive, and into the page is going to be negative. Then I2 is negative, and I1 and I2, I3 are really positives. Ampere's law also, this is really, this equation is valid for conductors and paths of any shape, and is gonna say the line integral around a closed path of B dot dl is gonna be equal mu 0 times I enclosed, and we can use this to calculate the magnetic field of conductors. Now here, for example, if we have a long cylindrical conductor, like the one shown here, it has a radius r and carries the current I. We will say that the current is going to be uniformly distributed over the cross-sectional area of the conductor, and in order to find the magnetic field, we apply Ampere's law, and we will find that B equals mu 0 I over 2 pi r over r squared. This is inside the conductor, and outside the conductor is going to be very similar to, the formula that we have before, mu 0 I over 2 pi r. Now for a solenoid, we will be able to have, a kind of helix winding of wires on a cylinder, and also we can calculate what is really the magnetic field of a solenoid, and the magnetic field of a solenoid is going to be B equals mu 0 n over times I, and n it is number of turns per unit length, and the magnetic field inside a solenoid, it is uniform. Okay, here this is okay, for this is like, just read this one here, just for the last part here, I will say Paramagnetism and diamagnetism. This is like a classification for material when an external magnetic field permeates a paramagnetic material. The result is that the magnetic field at any point is greater than by a dimensional factor. It's not dimensional, dimensionless. It doesn't have dimensions, and that is called relative permeability of the material. Now here we are listing some of the permittivity and relative permittivity. And this is here for the ferromagnetic materials, which we have really the domains that they are going to cause the material to be magnetic material, and we can magnetize. Okay, let me go over some of the most important problems here. These really good, good questions. Here we have an alpha particle. You need to know that the alpha particle is having a charge that it is plus 2e, and sometimes also you need its mass. Then we should know the mass as well. And an electron move in opposite directions from the same point, each with the same speed, which is 2.50 10 to the 5 meters per second as in the figure. Find the magnitude and direction of the total magnetic field by these two charges produced at point P, which is 8.65 nanometers from each charge. You might have 3 particles or 4 particles. Then what you need to do is you're going to calculate the magnetic field for each with its direction and then find the resultant. Now this is for a charge, is going to be B equals mu 0 over 4 pi q v times unit vector r divided by r squared. Mu 0 is the magnetic constant, and it has it has 4 pi 10 to the negative 7, and it has units Tesla times meters divided by amperes. Now B for the electron is going to be mu 0 over 4 pi q v times 1. The unit vector r, it has a magnitude 1, and sine 40, because look here, if you look at the diagram, this one is 140, then this one is going to be 40, and this is really the electron. And the direction, between the velocity, the green, and the blue that I did draw is 40. And the distance between them, it is 8.65 10 to the negative 9 meters, because it was given in nanometers. For the B for the alpha particle, it is again mu 0 divided by 4 pi, and it is 2 times q, which is the charge of the electron, times v1 times sine 140 divided by 8.65 10 to the negative 9 meters all squared. For the direction, the right hand rule, and as v goes to the direction of r, for example, for the electron, then we will find that this is going to be into the page for a positive charge, and therefore is going to be out of the page for the electron. For the alpha particle, it is going to be, of course, like v going to the green is going to go to the blue, and then my thumb is going to point out of the page, and then if I wish to calculate what is the total magnetic field, then I will say it's the magnetic field of the electron plus the the magnetic field of the alpha particle. I added here, and then finally it's gonna be the total is gonna be B 1.03 10 to the negative 4 out of the page. And then when you are going to be asked about the magnetic field, you should call the direction and the magnitude. Now here we have an electron and a proton are each moving at 735 kilometers per second in perpendicular paths as shown in the figure. At the instant when they are at positions shown, find the magnitude and direction of the total magnetic field they produce at the origin, the magnetic field and the electron produces at the location of the proton, and the total electric force and the total magnetic force that the electron exerts on the proton. First, of course, again, the magnetic field of the proton, it is mu 0 over 4 pi v times unit vector r divided by r squared. And here we're going to have replace the cross product by v times r, which is here 1, okay, sine 90. And of course the distance is 4, and this is into the page. For the electron is going to be mu 0 4 pi, again v dot r unit vector, and the distance is going to be 5, and it's going to be also into the page. And then I'm going to say B is going to be the total for both. And then I have calculated here the magnetic field to be 1.21 millitesla into the page. The second question, the magnetic field of the electron produces at the location of the proton. Then the electron, we're going to find what is really the, I will say at here, at the location of the proton. Then here we need to calculate first what is really the that distance, and that distance is going to be square root of 25 plus 16, which is 41. Then it is the square root of 41 nanometers. And the angle is going to be, now my R is going to be, 180 minus arctan 5 over 4. And we can calculate the angle as 128.7. And then I will be able to calculate the magnetic field that caused by the electron at the position of the proton. Now, if magnetic is going to be QVB sine 90, and that is really, and it's going to be in the positive x direction, using again the right hand rule. Okay, for the electrical force is going to be 1 over 4 pi epsilon 0 E squared divided by R squared, and that is going to be the calculated value for the electrical force. Now, long straight wire lies along the z-axis and carries a 4 ampere, like this is x, this is y. In the plus z direction, find the magnetic field, magnitude, and direction produced at the following points by a 0.5 millimeter segment of the wire centered at the origin. I is 4 and L is 0.5. We want to find first at x equals 2 meters, y 0, and z 0. dB, it is mu 0 over 4 pi I L cross R unit vector over R squared. This is for finite. 0.5 is going to be for delta L. 0.5 is going to be B is going to be mu 0 times I times delta L, R unit vector over R squared. And then here I can replace the unit vector by R, this by the unit vector. The unit vector itself, it is r divided by r. Then here I replaced r u0 here over 4 pi, and then it's going to be r cubed. Now I is in the z plus z direction, and delta L, it is in the k direction because it's along the z. And then I will find the field point at the x, which is 2 meters, y is 0, and z is 0. Now r, it like you can write it in the ijk form, and then you're gonna first have the calculate delta L cross r. Here you need to pay attention that you will multiply two numbers, but you're gonna multiply the two unit vectors k times I cross, of course, cross I. And remember the rule here, it is when you k time across k cross I is gonna give you j. And that is, when you multiply the numbers, it is 110 to the negative 3 square meters times j unit vector. And then I did calculate here the whole expression. And finally, I will find it 510 to the negative 11 Tesla j. For the second point, it is when b, it is x equals 0, y equals 2, and z equals 0. Then here, r, it is 2j, and the magnitude of it, of course, it is 2 meters. Again, I will do the same thing. Delta L times r is going to be the 0.510 to the negative 3 times 2k cross j. If you look again, k cross j, you're gonna go opposite direction here. I, j, k. Then if we are going to go k cross j is gonna, if we are going to go against the direction, then it's gonna give us negative I. Again, I did complete the calculation, and I have here negative 5, 10 to the negative 11 t Tesla times I. The last one, not the last one, C. X equals 2, y equals 2, and z equals 0. Then here what I did is, what is it? Yeah, it is r equals 2i plus j, and then r is going to be square root of 2 times 2. We are using the Pythagorean to find the magnitude of it, rx plus ry. And then here I did find delta L cross r, and then finally I was able to calculate what is really the field. Now the last part is asking about x0, y0, and z equals 2. Then now this is going to be k, of course. And when they are parallel, k cross k is going to be 0. Then the magnetic field is 0. All right. The next one. This one is a long straight wire lies along the y-axis and carries a current I equals 8 amperes in the y direction as in the figure. In addition to the magnetic field due to the current in the wire, a uniform magnetic field B0 with magnitude 1.5010 to the negative 6 Tesla is in the positive x direction. What is the total field magnitude and direction at the following points in the xz plane? Okay, and then here I have the points, and first I need to set my equations, and then I'm gonna go back to the B wire. It is a mu 0, times I divided by 2 pi r, and then at 001 meter, Okay, B is gonna be B0 minus mu 0 I over 2 pi r. That, okay, and that is here when we go to 0, 0, 1 meter. Okay, where is that? 0, 0. Okay, 1 meter. Okay, that is gonna be here at the Z. And then when we will say the current is going downward, okay, the current is downward, then according to the, that B here is going to be in this direction. Therefore, what we did is we subtracted B0 minus mu 0 I over 2 pi r I. Then we subtracted. That one is negative I and this one is positive I. Therefore, this is what we have. Now at 1 meter 0, 0, then now the X is 1 meter. Okay, then I am here. And then the field is going to be this way, is going to be this way. And then I will have the, B0 plus mu 0 I k, because now it's pointing along the positive z axis, and therefore I will say the magnetic field is going to have a component along the x-axis and a component along the k, the z-axis, and then I can actually again using Pythagorean to calculate what is the magnitude of the field and what is really the angle. Remember, the last one here, it is x equals 0 and y equals 0 and z equals negative 2.25 meters. Then it's z here is going to be on this point here, and that is going to be this direction. Then it's going to be, both of them are going to be in the same direction, and they're going to be added together. Here, this is like mostly like conceptual. Two very long insulated wires perpendicular to each other in the same plane carry currents as shown in the figure. Find the magnitude of the net magnetic field these wires produce at points P and Q if the 10 ampere current is to the right or if it is to the left. Okay, now the equation, it is F over L equals mu 0 I prime I divided by 2 by R. On the top wire, F over L is going to be mu 0 I squared over 2I, 2 pi, 1 over D minus 1 over 2D. Okay, why is that? Because the current here, the current in the middle is gonna be opposite, and that here we are going to find that force is gonna be upward because they are really repelling, and they are in opposite directions. On the middle wire, the magnetic force cancel because, okay, the forces, they're going to be in opposite directions. On the bottom wire is going to be like the same like the first one, but downwards. This one about a circular loop where we have to calculate the magnitude of the magnetic field at point B of the figure in terms of R, I1 and I2, and like when the expression when I1 equals I2, what is gonna be like the magnitude of B. Now here we're gonna calculate the magnetic field vector produced by each wire and then add to get the total field. And then here we're gonna have it dissected into parts. Then I'm gonna say the first one on the top, I'm gonna also make it A, B, and C because I have straight and then I have circular. A and C, they are long straight sections, and then I will say DL cross R, they are going to be 0, and then DB is going to be 0. Then they will not be participating in the, they're going to be either in the same direction or opposite directions. For the circular, DL over R times R is directed into the paper, for all segments, and then B is directed into the paper. And again, this is using the what is called the cross product rule. Now the vector sum of all of the dB is gonna be by adding, since all of them are in the same direction. First, I need to find RDL sine theta, and that is going to be when theta equals 90, R will be uppercase R, then I will say RDL. I will put it here into the expression, and then I will integrate, and then finally, we're going to find that this is going to be mu 0 I1 over 4I, the expression that we are going to find for the magnetic field at the point B. Now, pi r, of course, is the length of the wire in the semicircle, and this is the reason why we have this is like the integration of dl. And now, since the straight segments, they don't contribute, then it's going to be B1 mu 0 I1 over 4 pi. Now also we can follow the same steps for the lower one, and then B2 is going to be mu 0 I2 over 4R, and it's going to be out of the paper. And then I will say B1 and B2, they're going to be in opposite directions. Then I will have I would say the what is called the resultant magnetic field is going to be the difference mu 0 I1 minus I2 over 4 pi. And then when I have I1 equals I2, then B is going to be 0. This is Ampere's law, where we have in the figure a cross-section of several conductors that carry currents through the plane of the figure, and the currents, they have magnitudes. I1 is 4 amperes, I2 is 6 amperes, and I3 is 2 amperes, and the directions shown here for paths labeled A through D. We want to find the integral of B dot dl for each path, and we're going to have that each integral involves going around the path in the counterclockwise direction, so that we will be able to find out which one is going to be positive, which one is going to be negative. Path A, we have no current, I enclosed, then B dot dl is 0. For path B is this one here. We have the current, that one is going into the page, and therefore is going to be negative I1, and that is negative 4 amperes. Then B dot dl is going to be minus mu 0 times I, which is minus mu 0 times 4 amperes. And that is the answer here, 5.03. For path C, I enclosed is going to be C. We have two currents, one of them negative, which is I1, and one of them is positive. Then negative 4A plus 6 4A, which is going to be 2A. And then we are going to say B dot dl is going to be mu 0 times 2 amperes, and that is going to be 2.51 10 to the negative 6 tm. Path D is going to be all of them together, and then it's going to be for I1 negative, I2, I3 positives, and then the result is going to be 4 amperes, and it's going to be 5.03 10 to the negative Tesla times meters. This one here about a solenoid. As a new electrical technician, you are designing a large solenoid to produce a uniform 0.150 Tesla magnetic field near the center of the solenoid. You have enough wire for 4,000 circular turns. The solenoid must be 55 centimeters long and 2.8 centimeters in diameter. What current will you need to produce the necessary field? At the center of a long solenoid, we're going to have a mu 0 Ni, and N capital or uppercase N, it's the number of turns, and L, it is its length. And then simply I is going to be BL divided by mu 0 times the number of turns. This is the last one. Here we have calculate the magnetic field, magnitude and direction at a point B due to a current I, which is 12.0 amperes in the wire shown in the figure. Segment BC is an arc of a circle with radius 30 centimeters, and point B is at the center of curvature of the arc. Segment DA is an arc of a circle with radius 20, and point B is at the center of the curvature. Segments CD and AB are straight lines, length 10 each. Now the magnitude of the field at the center of a circular loop, it is, we concluded that it is B equals mu 0 I over 2 pi A. Now each arc here, it is 120 degrees, therefore 120 over 360, it is 1/3 of a complete loop or complete circular. And therefore B is going to be 1/3 of a mu 0 I over 2 pi A, and that is going to be mu 0 I over 6 pi A. And then the B net is going to be the difference between the two magnetic fields, and the net field points into the page at P. All right, this is all for this chapter. I will leave the examples for you to read, and I did extra examples here so that you will learn from these. Thank you very much. Have a good night.